everyone, I am Dr.R.Selva Priya, working as an assistant professor in physics, Christian College of Engineering and Technology, Pottanjitram. Today we are going to discuss about the classification of magnetic material. Based on different material behave differently for the application of external magnetic field. Based on the response of external magnetic field, the material are classified into 5 different types. That is called dia, para, ferro, antiferro and ferrimagnetic material. Among the materials, the diamagnetic material do not have a permanent dipole moments. Others like a para, ferro, antiferro and ferrimagnetic material have own permanent dipole moments. Next, first one is a diamagnetic material. In the diamagnetic material, they do not have a permanent dipole moments. So in the absence of external magnetic field, they do not have a permanent dipole moments. So the diamagnetic material placed in an external magnetic field, the dipoles are induced. The induced dipoles are opposite direction to the external applied magnetic field. So the diagram indicates H is equal to 0 means there is no permanent dipole moments. There is no external magnetic field, there is no permanent dipoles. When we are applying an external magnetic field, the induced dipoles are created. The created dipoles are opposite direction to the external magnetic field. So, next is an effect of magnetic field. When the diamagnetic material is placed in an external magnetic field, it repels the magnetic lines of force effectively. Next, properties of diamagnetic material. We already know that the diamagnetic material repels the magnetic lines of force effectively, and the susceptibility is negative, and it also independent of temperature. The permeability is also less than 1, and that is no permanent dipoles are present in the diamagnetic material. And also when the temperature of the diamagnetic material will increases means it automatically converted into a normal material, and also it has a superconducting nature. Second is a paramagnetic material. The paramagnetism may be due to the presence of few unpaired electrons present in an atom. In the absence of external magnetic field, the paramagnetic dipoles are randomly oriented. Due to random orientation, the magnetization value will decrease. So, when we are applying an external magnetic field to the paramagnetic material, the dipoles are randomly oriented. Dipoles are aligned same direction to the external magnetic field. So, this alignment will increase the magnetization value. So, again the paramagnetic material will placed in an external magnetic field, it will attract the magnetic lines of force strongly. So when next the effect of temperature on the paramagnetic material, when the temperature of the paramagnetic material will increases means the randomly oriented dipoles are rearranged, and that is called randomized dipole direction, leading to the decrease in the magnetization value. Next, Curie's law. In the paramagnetic material, the magnetization of material is directly proportional to the applied magnetic field. The paramagnetic susceptibility varies inversely proportional to the absolute temperature, that is chi directly proportional to 1/T. Here the value of T increases means chi will decrease. This equation indicates the Curie law of paramagnetism. Next, properties of paramagnetic material. It attracts the magnetic lines of force strongly. It have a positive susceptibility value and have permeability is greater than 1, and it has a permanent dipole moments with spins are randomly oriented in nature. When the temperature of the paramagnetic material will increases means it will automatically convert into a diamagnetic material. Third is in ferromagnetic material. Ferromagnetism may be due to the presence of more unpaired electron present in an atom. So in the absence of external magnetic field, the ferromagnetic dipoles are aligned parallel to each other. This parallel alignment will produce a large value of magnetization. So even in the absence of applied magnetic field, the ferromagnetism will produce a large value of magnetization. So this phenomena is called spontaneous magnetization. So the diagram indicates the spin alignment in the ferromagnetic material. Next, effect of magnetic field. When the ferromagnetic material placed in an external magnetic field, it will become a very strong magnet. Next, properties of ferromagnetic material. All the magnetic lines of force pass through the ferromagnetic material. Its permeability is very much greater than 1. It has an own permanent dipole moments. When the temperature of the ferromagnetic material will increases means it automatically converts into a paramagnetic material. So, the nickel, iron, cobalt, steels are the example of ferromagnetic materials. Next, application of ferromagnetic material. The ferromagnetic material widely used in making a permanent magnet, electromagnet, transformers, inductor, and some magnetic storage devices. Fourth one is an antiferromagnetic material. In the antiferromagnetic material, the spins are aligned antiparallel manner with an equal magnitude of spins. These spins resulting in this alignment resulting in a zero magnetic moment. Even when we are applying external magnetic field, it has an almost zero induced magnetic moments. The diagram indicates the spin alignment in the antiferromagnetic material. Due to this spin alignment, even we are applying an external magnetic field, the induced magnetic moment is almost zero. So ferrous oxide, FeCl4, MnO4, MnS and some ionic compounds are the example of antiferromagnetic material. So next, properties of antiferromagnetic material. It has susceptibility is very small and positive. When the temperature of the antiferromagnetic material will increase, this means it automatically converts into a paramagnetic material. That particular transition temperature is called Neal's temperature. Fifth one is a ferrimagnetic material. Ferrimagnetic material is much similar to the ferromagnetic material. In the ferrimagnetic material, the magnetic dipoles are aligned antiparallel manner with an unequal magnitudes. This alignment will produce a large value of magnetization. The diagram indicates the spin alignment of ferrimagnetic material. This spin alignment, if you are applying a small magnetic field, external magnetic field to the alignment, it will produce a large value of magnetization. Properties of ferrimagnetic material. Its susceptibility is very large and it's positive. Beyond the Neal temperature, the time that is susceptibility decreases. The material have a low eddy current losses and it low hysteresis losses. They have a hysteresis loop in the form of square. It will have a low coercivity. Next, application of ferrimagnetic material. The ferrimagnetic material widely used in high frequency application and computer memories. Thank you.